pleasure to introduce our speaker this afternoon, Dr. Christine Baker. She's currently a postdoctoral research scholar at North Carolina State University and starts as an assistant professor in civil and environmental engineering at Stanford this summer. She earned a bachelor's degree in civil engineering from OSU and a master's and doctorate in civil and environmental engineering from the University of Washington. Her research focuses on wave breaking and circulation dynamics in coastal regions and their influence on sediment, pollutant, and particle transport. She investigates coastal dynamics and hazards using laboratory experiments, as well as numerical modeling and remotely sensed field observations. So please join me in welcoming Christine.
All right, hello everyone. Thanks for the introduction, and thanks for hosting me here today. I've had a great day thus far. So I'm going to be talking about work I did at the University of Washington with Melissa Moulton, Chris Chickadell, and Emma Ness at the University of Washington, Meg Paulson from the USGS, and Kate Brody from the Army Corps of Engineers. And this work today will be largely focused on flows within the nearshore region, specifically within the surf zone, where waves break along the coast, and how they can drive exchange with the inner shelf, offshore the surf zone to about 1.5 kilometers offshore. So why do we care about nearshore flows? As you can see in this image, as all you know, a lot of our population lives along the coastline, and due to this, we're very reliant on this region for recreation and commerce. We're also susceptible to the dynamics within this region, especially with sea level rise, and yet we're also responsible for the degradation of water quality within this region, which can cause harm to coastal ecosystems. Critical for human and ecosystem health, nearshore flows can help determine the fate of material within the nearshore. So this material could be pathogens and contaminants that increase the risk of illness for recreational swimmers. It could be terrestrial runoff that can lead to eutrophication and hypoxic conditions. Additionally, species inhabiting the nearshore actually rely on nearshore flows for recreation and recruitment. And nearshore flows can dramatically alter the shape of our coastline by transporting sediment. So in today's talk, I'm going to be focused on a nearshore flow that drives exchange between the shoreline and deeper waters, and those are by rip currents. So rip currents are narrow and seaward-directed flows extending from the surf zone and into deeper waters, and you can think about them as conveyor belts between these two regions. Relatively speaking, we know a lot about bathymetric rip currents. Bathymetric rip currents form due to wave breaking patterns on a longshore variable bathymetry. So for example, if you had a bar with a channel in it, and they can form at these fixed locations over relatively long timescales on the order of hours to maybe even days. In contrast to that, we know less about how transient rip currents form. So transient rip currents are often characterized as these ephemeral ejections offshore that can form on alongshore-uniform beaches with no preferred alongshore location. And the processes leading to how transient rip currents form will be the focus of my talk today. So I'm going to go into a bit of detail about how we hypothesize that they form. So we think that transient rip currents form during a certain type of wave-breaking pattern, and to explain that, I'm going to first contrast them with another type of wave-breaking pattern. So if you've gone to the coast and you looked out and you see waves breaking at the coast at similar times, maybe it's a swell arriving from a distant storm, you might say that these waves are fairly unidirectional, or their energy is spread narrowly in direction. And so to demonstrate this, I have a directional spectrum. This is showing you how energy, which is the brighter regions in the plot, is distributed in frequency, which is the radial distance, and direction, which is the azimuth. And here, for these unidirectional waves, we have this very narrow-banded spread in direction. And note that these are from the lab experiments we'll talk about today. So in contrast to that, if we have our energy spread very broadly in direction, we might see a different wave-breaking pattern. So during directional spread wave conditions, waves can break at the beach along finite lengths, which we call short-crested wave breaking. And sometimes you can associate this with a local wind sea, for example, that has more choppy waves. And so short-crested wave breaking is thought to be important for how we drive transient rip currents. And that's because during short-crested wave breaking, you have a force associated with the breaking wave that occurs in one location, but not another. And this transition from a broken to unbroken water surface can lead to the injection of positive and negative vertical vorticity at crest ends. Or you can think about them as horizontally counter-rotating eddies. And I'll note here, because some people get stuck in this, horizontal eddies is the vertical vorticity component. All right, so these small-scale eddies within the surf zone, energy associated with them can be transferred to larger scales through an inverse energy cascade, and we'll get to that more later on in the talk. But resulting in these large-scale rotational motions. And these large-scale rotational motions, these eddies can evolve within the surf zone and mutually affect offshore as a transient rip current, resulting in these dramatic plumes of dye that you see in this image that can be exchanging material into deeper waters. And so these surf zone eddies that you see in this image and transient rip currents occur on timescales of minutes to maybe tens of minutes. What we coin as low frequencies, which is much shorter timescales than, say, bathymetric rip currents, but much longer timescales than individual breaking wave crests. So while the processes that lead or connect the directionally spread wave field to the formation of these transient rip currents are broadly discussed within the literature, there's actually little observational evidence of this process. And that's for a number of reasons. First, it can be hard to isolate this process in the field. You can't control the bathymetry and the wave conditions. And second, this process is temporally and spatially complex, so it can be hard to observe with traditional observational techniques. So for our work, we decided to study this process in the laboratory, heavily utilizing remote sensing. So this is the structure of the talk today, and I've broken it down very much so in parallel of how I introduced how to make a transient rip current. But before I jump into the findings, I'm first going to give you an introduction to the experiments. So we ran a month-and-a-half-long campaign of experiments at the O.H. Hinsdale Wave Research Laboratory at Oregon State University, which is a very large-scale directional wave basin. It's about the size of an Olympic swimming pool. And I know that some people in this room are very familiar with this facility. And we tried to make the basin the most ocean-like as we could. And some aspects were ocean-like and some weren't. One thing we did is we wanted to increase the width of the surf zone, so cause waves to break farther offshore. And so we constructed an alongshore-uniform concrete bar on the 1x10 slope. The facility has 29 wave paddles in the back of it, and so they can move at different times and based off of theory and create directionally spread sea states that resulted in these short crested wave breaking patterns that you can see in this image and eventually led to transient rip currents. So for the experiments, we ran 70 45-minute tests with 25 different wave conditions where we varied the wave height, the directional spread, the peak period, and the mean water level. And what I'll be talking about the most today is different directional spreads and 2 different wave heights. To measure these these experiments, we used a combination of in situ sensors and remote sensing. And so this is just a video of a directional spread sea state in the lab. And we deployed co-located pressure sensors and ADVs within the surf zone, which are in red here, and redeployed them within the inner shelf. And we also had 15 wire resistance gauges mounted to the bridge of the tank, which gave us the offshore wave conditions. To measure the water surface across the tank, we had a LiDAR. And often LiDAR is set up to spin in the cross-shore direction. But since we're interested in the along crest variation of the wave field, we set up the LiDAR so it's 32 beams spun in the alongshore direction, which collected snapshots of the water surface at 10 hertz. But the technique I'll be relying on the most today for this talk is from imagery. So we had 3 cameras mounted to the ceiling of the tank, and they took images of the water surface from slightly different angles at exactly the same time. And using matching features between these frames, we can make maps elevation maps of the water surface with stereophotogrammetry. And you can think of this as just as if you were to look out at something with two eyes, you can tell distance better than just one. All right, so here's an example of a stereo reconstruction on the bottom. It has the longshore along the x-axis and the crossshore along the y-axis, and it's colored by water surface elevation, where higher elevation features are brighter. And then the orthorectified image at the same time is just on top. And what you can see in this video is that we are able to reconstruct the water surface fairly well within the surf zone of the tank, where there was lots of surface features to match, but we couldn't do it offshore of it. And so in this video, I have the location of 2 in situ sensors, and I'm now showing you time series comparison for them. The black is the pressure sensors, the red is the, stereo, and the blue is LiDAR in the offshore edge of the surf zone and inner surf zone. And so a lot of the initial work for this project was doing comparison between these measurement techniques. And what we found is they're generally consistent within the surf zone, inner surf zone, with some differences that are partially attributed to differences in measurement techniques. All right, so that was the fast overview of the experimental setup. And now we're going to think about the wave breaking patterns. So in particular here, we're wondering, we often describe our wave field in terms of, say, bulk characteristics, wave height, peak period, maybe mean angle, and directional spread. And so here in particular, I'm going to zero in on how does changing this directional spread alter the along crest length and the number of crest ends, because this can alter the number of locations that we get this injection of vorticity. All right, but in order to assess this relationship, we need to be able to identify wave crests. And so to do that, I'm using imagery. And if you were to go to the beach and pick out the breaking waves, you pick them out as the bright features. And so we're just using a similar concept to that by thresholding the imagery based off of pixel intensity. However, when waves break, they often leave behind residual foam, which is not an actively breaking wave. And so we wanted to remove those features. And to do that, we picked out the highest elevation regions in the stereo reconstructions, and we're able to constrain our identified wave crests, which you're seeing in the bottom here. And then I can go in and I can measure that crest length, and I can count the number of crest ends. And I can do that for a bunch of different wave conditions. So this is a near unidirectional case on top, a moderate directional spread in the center, and then a large directional spread case on the bottom. And for each of these trials, I'm going to get a distribution of crest lengths. And what I can do is just go in and compute the average values for the crest length and number of crest ends per surf zone. And here's just a plot of it. And so what these plots are showing is that as you increase the directional spread, you see a decrease in crest length that has little dependence on wave height. And you see an increase in the number of crest ends within the surf zone with some dependence on wave height. And as I alluded to at the beginning of this talk, this relationship isn't totally unexpected. As you increase the directional spread, you see a decrease in crest length. However, this hadn't been shown with observations before, and as part of this work, we compared it with analytic solution for estimates of crest length based off of linear wave theory, and saw that at least on first order, it described the patterns that we saw in the tank. All right, so we talked about how the directional spread is related to the breaking crest characteristics, and now we get to think about how these breaking waves generate eddies or vorticity. In particular, in this section, we're going to talk about how, what is this, we're going to estimate this breaking force term and describe how it varies along the wave crest. I'm showing this breaking force as these yellow arrows here, and then see what we can say about that and how it's related to the vorticity that's generated at crest ends. But before I jump into that, I'm just going to take a step back and say, what is this breaking force term that I'm going to be talking about in this section? You can think about the breaking force as kind of like pushing on the water. And during short-crested wave breaking, you're pushing on the water in one location, but not another. And so this transition from this non-zero braking force to zero braking force can generate this vertical vorticity. And you can think about the pushing as kind of like maybe a paddle or a roller. So I have a fun video that was taken by my colleague where she put, she had water with dye in it, and she's going to take this roller, she's going to insert it and push on one location, but not another. And you can see it generates these beautiful counter-rotating vortices. As a fluids nerd, I always like this video. But you can think about the analogy for this section of the talk as describing this ruler, and how pushing with this ruler generates the vortices. All right, so now you have an idea of what the braking force is. We can write it in terms of our depth average momentum equations, and write it that in terms of rotational components by taking the curl of it. And ultimately, what I want you to get from this slide is that on temporal and spatial scales of individual wave crests, we can say that there's this approximate balance between the time rate of change in vorticity and this curl of the wave braking force. And I'm going to coin that as the vorticity forcing for the rest of this section. So we'd like to estimate this with observations. And in order to do that, we can write the braking force in terms of the cross-crest gradient and the radiation stress, which, doing some math, you can get to, it's approximately equal to the depth average dissipation over the water depth times the bore celerity. And so in order to estimate this, we need a number of, per se, ingredients at each cross-crest transect. And so we need information about the roller geometry, including its length and its angle. We need its wave period, water depth, and the bore celerity. And this gives us an estimate for the braking force at one cross-crest transect, and we're going to go all the way along the crest and estimate this value. All right, so what does this look like in observations? To describe this, I'm going to tell you the story of just one wave crest that I've identified using the method that I talked about in the previous section. So we're going to go in and pull cross-crest transects all the way along the wave crest. And we can pick out the toe, which I'm showing in red, and the crest, which is in blue. And using that information, as well as the peak period, we can get an estimate of the along crest profile and the dissipation, which I'm showing on the right-hand side. And from that, to get to the braking force, we need to estimate the bore celerity. And so I've tracked waves through frames to estimate the bore speed. And using that information, as well as the water depth and dissipation, I can get to the braking force, which I'm now showing as overlaying on this, the toe of this wave crest, and I'm showing the along crest profile here. And one key assumption I'm making at this part of the analysis is that outside of the region that we have identified as a braking wave crest, the braking force goes to zero. All right. Lastly, to get to the vorticity forcing, we can just take the along crest gradient and the braking force. And now it's shown over this image. I'm showing the along crest profile over here. And as you can see, for this case, it's fairly consistent with the schematic that I was showing. You see positive vorticity on one side and negative on the other. However, this is really not the full story of this wave crest. This is just one instance in time. And in reality, this wave has broken at the outer edge of the surf zone and is doing so, and it's propagated through the surf zone. And in doing so, it is evolving. So if you watch this video as many times as me, you might notice that from one frame to the next, there's fairly similar patterns in the along crest or in the vorticity forcing. However, you might see that it's fairly different in the outer surf zone than the inner surf zone. And we'll get to that more later. But in reality, that's just one wave crest, and it's actually kind of a simple case. And we're actually in an irregular directionally spread sea state. And so if I estimate this value on all the wave crests, I can see that it varies dramatically from one wave crest to the next, although there are some similar patterns. But for now, I just want to get this bulk estimate of how much vorticity forcing input is there within the surf zone. And so to do that, I'm just summing up the absolute value of this vorticity forcing across the surf zone. And I'm getting this, I'll get this time series essentially of it, of the total vorticity forcing. And here I'm just showing the median total vorticity forcing for a bunch of different cases. And what you can see here is that as we increase the directional spread, we get more of this input of vorticity forcing within the surf zone. And so, which does vary based off of wave height, so you can think about the amount of energy in the system. And we think this can help describe, fill in the picture of why we might expect to see more low-frequency eddy activity within the surf zone for increasing directional spread. All right. So the other component that I was interested related to the braking force is trying to get at what length scales we may be injecting within the surf zone. And what I mean by that here is that if the braking force profile is constant along it, it may inject very different length scales than if we have this really a long crest varying braking force profile. So in order to assess this, I took the average of thousands of wave crests, or let's see, I normalized them from 0 to 1, and then I took the average of thousands of wave crests in the outer surf zone, which is on the left-hand side, and the inner surf zone, which is on the right-hand side, where I've divided it by the deepest region in the wave trough. And here I'm plotting the braking force on top and the vorticity forcing on the bottom. And from these plots, you can pick up a few things. First, you can see that it's kind of consistent with the story that on average, there's a positive vorticity forcing on the right-hand side and negative on the left-hand side. And here spikes on the edges. But what you can also notice is that the along crest profile of the braking force looks fairly different in the outer surf zone than in the inner surf zone. So if I zoom in on this plot, you can see this results in this non-zero vorticity forcing across the entire wave crest in the outer surf zone, where we have this region that is near zero across most of the wave crest in the outer surf zone. So this suggests that there may be some, we may see some different length scales injected at different regions of the surf zone. All right, so in this section we talked about the total vorticity forcing per surf zone, and we saw that it increased with increasing directional spread. And then we looked at the average braking force profiles and saw that they look very different in the outer surf zone than the inner surf zone. But as we looked at earlier, if we look at them on a wave by wave basis, it's actually way more complicated. All right, so we talked about how directional spread alters the braking characteristics and how that might change the eddies that are generated. Now let's think about, okay, once we've generated these eddies, what do they do? In particular here, I'm curious, do these eddies evolve similar to two-dimensional turbulence? So typically we think of our world in three-dimensional, in 3D, where we see three-dimensional turbulence, where energy is being transferred from these larger scales to much smaller ones through a direct energy cascade. However, if you took out one dimension and we're in a strictly two-dimensional world, you'd actually see the opposite. You'd see that energy is transferred from these smaller scales to larger ones through an inverse energy cascade. And an inverse energy cascade has been observed in the ocean and atmosphere in systems that have much larger horizontal length scales than vertical length scales. However, these systems are typically described as quasi-two-dimensional, where they actually have a split energy cascade, where the energy that is not transferred to larger scales is transferred to smaller ones through a direct energy cascade. So we think that maybe this applies within the surf zone. where when we have these eddies injected by breaking wave crest, some of that energy is going to smaller scales and it's being dissipated. But possibly for some wave conditions, we might see that some of the energy is being transferred to larger scales. And this may explain why we see the presence of these large-scale rotational motions in the surf zone that are important for dispersion and can also lead to transient rip currents. So we're going to investigate if we see evidence of that. However, in order to do that, we need much higher resolution velocities than we can just get from our in situ sensors. So I'm going to be essentially tracking foam and imagery to estimate the surface velocities. And doing this is not a new concept to the nearshore world. It's been done to estimate mean velocities in the surf zone. However, often it's hard or it's challenging to get higher frequency velocities than that because you have these bright breaking waves going through your frame that can bias your signal shoreward. So in order to estimate the surface velocities, I'm using particle image velocimetry, and I'm estimating the surface velocities at each time step. And then I'm going in and I'm removing any of these velocities that are associated with breaking waves that I've identified in the first section of my talk. And then I'm going in and taking an 8-second median filter of these velocities. And so this is going to be a video, it's a quiver plot, and it's colored by vorticity. And what you can see in this video is there are coherent rotational structures. They are evolving in time. Sometimes they appear and they disappear. And sometimes you might even see that they are vecting along the surf zone. And I landed on this processing technique that I was describing by comparing them with the surface velocities with in situ sensors. And so I'm just plotting this time series comparison on the right-hand side between the in situ, which is pink, and the PIV, which is in black, in the outer surf zone on top, and the inner surf zone on the bottom for the cross and alongshore velocities. And what we saw is that we found the best agreement for the alongshore velocity component between, I'll note, the surface velocities and near bottom in situ velocities. And so for this analysis that I'm going to talk about, I'm only going to look at the alongshore velocities, and I'm going to look specifically in the center of the tank. All right, so what is this analysis? For the analysis I'm going to describe, I'm going to be focused on, just for demonstration, 3 different wave conditions with all the same wave height for this small, moderate, and large directional spread wave case. And these are just snapshots in the center of the flume from the PIV. All right, and for this analysis, to see if we see evidence of energy transfers to different scales, I'm going to use a structure function analysis, which is essentially I'm just going to, for one given cross-shore position, I'm going to take a transect of the alongshore velocities, compute the difference between the alongshore velocities at different legs, and then do that at each section, at each time step, which is and raise it to the nth power, and do that each time step, and then I get the structure function at each cross-shore position. And most of the analysis I'm going to show you, or the analysis I'll show you today, is I'm taking the surf zone average value. But for this, you can just, I'm going to walk you through how to interpret them. And one way, at least I find relatable, is it's kind of similar to a wave number spectrum. All right, so first we're going to look at a second order structure function. And this is like an idealized schematic of what it might look like in the surf zone, with the leg along the x-axis and the structure function magnitude on the y-axis. And so for some eddies injected and an intermediate length scale, which I'm showing with this yellow region, the structure function is going to scale with the leg to the 2/3 over both the direct and the inverse energy cascade region. And then at some leg, it's going to flatten off, saying that flows are no longer correlated at this length scale. All right, so what does this look like in observations? So here's the surf zone average structure functions for the 3 different wave conditions I'm showing on the left-hand side. And on the top, you can see the unidirectional wave case. And so at legs greater than 30 centimeters, the structure function is flat, indicating that flows are uncorrelated, which is consistent with our story that we need crest ends to eject vorticity. However, you see for the moderate and large directional spread case that the structure function scales over more similar to what you'd expect for energy transferred to different length scales. And the only other study who has looked at the relationship between directional spread and the presence of an inverse energy cascade used numerical modeling and a second order structure function. However, as we talked about in the previous section, we don't actually have our injection length scales very well described in this system. And so I can't confidently say that this provides evidence of an inverse energy cascade because both the direct and inverse energy cascades scale similarly in the second order structure function space. But luckily we can compute a third order structure function that's going to look different for the direct and inverse energy cascade. All right, so for the third order structure function, you're going to see a negative and linearly decreasing slope for the direct cascade and a positive and linearly increasing slope for the inverse energy cascade. All right, so here's the third order structure function estimates in the experiments. And what I'll note here is we are no longer in log space, like the second order structure function. So for the unidirectional wave case, we see that it's flat, it's fairly consistent, it's uncorrelated. However, for the large directional spread cases, kind of looks like the schematic I showed, where we have this negative and linearly decreasing region, and this positive and linearly increasing region, which is consistent with an inverse energy cascade. So, and that's between about 2.5 to 5 meter length scales, which is approximately equal to the width of our surf zone. However, interestingly, I would say, we actually don't see the same pattern for this moderate directional spread case. We see that the structure function is negative and doesn't have this positively increasing region consistent with an inverse energy cascade. All right, so bringing this back to the initial hypothesis, this suggests that, okay, for the large directional spread cases, we can say that, this provides evidence that, energy is probably injected at some scale, and we see that the structure function scales similarly that you'd expect to an inverse energy cascade. However, this isn't true for this moderate directional spread case, which I found very interesting. And I think possibly the reason for that is that we're having injection of vorticity at larger length scales, potentially. As we talked about in the previous section, where especially in the outer surf zone, if the injection length scales scale with the wave length we're having, or the crest length, we're having longer crest lengths for this moderate directional spread case. Or it could be due to other dynamics within the system. And I think this is actually something interesting to look into in the future. All right, so in this section, we looked at if we saw evidence of energy transfers within the surf zone. And specifically, we saw an inverse energy cascade. And what I showed here is that it actually really varies based off of directional spread. And bringing this back to the initial question here, I said, how do we get from this directionally spread sea state to transient rip currents? And in the first section of the talk, we showed that as you increase the directional spread, you'd see a decrease in the average crest length and the number of crest ends. And then we looked at the vorticity forcing. And we saw that as we increase the directional spread, we see more of this total vorticity forcing input into the surf zone. But if we look on a crest by crest basis, we see it's actually pretty irregular. And so you can think about this as all of the input into the surf zone, and where the outcome is that we saw that the surf zone was low frequency flow is consistent with an inverse energy cascade, at least for the largest directional spread cases, which can explain how we get these low frequency, large scale eddies that can result in transient rip currents and are important for tracer exchange. But as you might have noticed, I didn't actually get to transient rip currents, ejection events in this work, and connecting that into the relationship with directional spread. However, we saw ejection events within the facility, so potentially what could be done is seeing what I've visually seen is that when you see ejection events of these wiffle balls that we seeded within the tank, now that I have these surface velocity fields, I can see that there's always strong offshore flows during these occurrences. However, potentially there are other tools that are also useful for looking at this. So I wanted to highlight some work that I'm doing with a student at the University of Washington, M&S, who has been simulating the lab experiments with numerical modeling, with phase-resolved numerical modeling. And so here's just a video. This is of the vorticity field within the surf zone, and this is the lab scale, just much wider. And I'll play the video because it's kind of cool to watch. But what she's been doing is looking at the relationship between directional spread and exchange driven by transient rip currents within the lab, and she's also compared some of the metrics that I talked about in this talk with numerical simulations. And as you can see, these transient rip currents are also often these negative and positively signed ejection events. And as I mentioned at the beginning of my talk, we care about this because it helps us understand tracer exchange within the near shore. But what I didn't cover, which is normally a clear motivation for understanding rip currents, is that they're a hazard for recreational swimmers. And so some work that hopefully will be coming out soon from a student that I've been working with at George Washington University, Audrey Casper. She's been comparing NOAA's rip current hazard forecast, so they give a probability of hazardous rip currents. And she's been comparing them with lifeguard observations of different types of rip currents and parameterizations based off of physics, bathymetrics, and transient rip currents occurrences. And what she's interested in is if NOAA rip current hazard forecast models can predict when we see hazardous transient rip currents, because often they're trained on systems where there's more bathymetric rip currents. And she's seen that this skill isn't excellent. And lastly, I just wanted to end my talk with all the work I was talking about here is from work I did at the University of Washington during my PhD, but since then I've been spending 8 months now in a postdoc where I've been focusing on slightly different topics. I've been working on storm impacts on sandy beaches, and which is 2 projects. One of them is looking at infragravity wave dynamics during storms, and it's using a data set from the sand motor in the Netherlands, where the engineer in me really loves this. They constructed 2 dunes slightly closer to the mean water level line. And they, so that during high water level events, they actually got impacted. And so they're actually able to observe the erosion of this dune during several storms. And so if you're going to ocean sciences, you'll hear me talk about that there. And then the other project I've been doing is using similar methodology that I used in the lab using stereophotogrammetry, but instead now looking at the beach face. So we have a camera system that's deployed at Masonboro Island. And we're interested in seeing if we can capture the beach recovery process and looking at the alongshore variability in it. But we're still waiting for our perfect storm. Or I guess I shouldn't cross my fingers there, but we will see. If anything, it'll be interesting to look at alongshore variability. Okay, I will end the talk there.
You focused on the dynamics of the waves, and I'm just thinking, if someone is out surfing, the waves are certainly important, but you kind of know that there are different breaks along a given beach that change the dynamics of what's going on in terms of where waves crest and all of that. Can you talk about how all of this interacts with the form of the ocean bottom, and particularly how quickly it changes?
Yeah, I mean, I think that's a great point, because I'm working in this alongshore-uniform system because I want to focus on these transient processes. But on many beaches, there's alongshore varying features, right, that cause these persistent breaks, like you were referring to. And so, which often leads to these bathymetric rip currents, right? And so I'll say on some beaches, maybe they're more dominated by these bathymetric rip current features. And then so there's some others you might see more, for example, in Southern California is where this work on transient rip currents initially came out, because they wanted to explain why they saw rip currents when there wasn't variable bathymetry. And potentially there's some intermedium where both are important, and I think that's not super well established exactly right now. And as far as how the beach evolves, I would say that there is some work previously that came out that was looking at how eddy processes can, like if you have this eddy field, it can eventually lead to this irregular bathymetry. So there is some coupling in that system, although I would say, like, as far as thinking about this particular mechanism, it's not as well established at this time.
Thank you.
Yeah.
Nice talk. That was great. Yeah, so many things that you're looking at. Very cool. And many things that you're looking at, people have tried in the past for years to do and couldn't do. So it's really cool to see this sort of coming alive. So your length scales of the vorticities that are generated scale differently depending on their wavelength. I mean, what are they scaling with? Is it scaling with the amplitude, and then as you get an inverse cascade, does it scale with the wavelength, or is it scaling more with the surf zone width?
Okay, let me see if I can make sure I
Something
answer this
else.
appropriately. We'll go back to structure function. Maybe here. So I guess the injection itself of vorticity driven by waves, I think has been kind of an open question. Initial work thought that, yeah, for, maybe I have to go back here. Let's see. The initial drawings I showed were for one of the original papers talking about this process. And what they suggested is that, for these short waves, you have this along crest varying profile. And then for longer waves, maybe it's uniform across the entire wave crest. You have this alongshore varying breaking force at some length scale. And so in this framework, we might think that vorticity is generated, there's some maximum length scale that can be generated that's based off of where you see a gradient in dissipation. What I was seeing from the lab experiments is that maybe this conceptual model isn't, maybe this works in the inner surf zone, but in the outer surf zone we might see it's varying along the entire wave crest. So in the case that it's varying along the entire wave crest, it would scale with the length, the longshore length.
The crest length.
Yeah.
So let's go with the crest length, not the wavelength.
Yeah, well, yeah, it's the breaking crest length, which you can, if you describe your wave field, that's going to be your longshore wave number that it will scale with.
So that depends then on the directional spring.
Yes,
Because that could
exactly.
That. But
Yeah.
those scales are relatively small compared to, let's say, surf zone width scales. So would they be, that inverse energy cascade will take many orders of magnitude compared to the direct cascade, which goes from short scales to even shorter scales. Is that right?
So for this large directional spread cases, I think that's completely right. Even if you're injecting, on a scale that's about half the width of the breaking crest, it's still much smaller than these maximum length scales in the system. But for these smaller directional spread cases, they actually have pretty large length scales.
But less.
But yeah, I do think that there's some open questions. For example, some work I did that I didn't show today is you could make some arguments that instead of this abrupt demarcation where you have this breaking force and then it goes to zero, maybe it's more gradual and that would change your length scale dependencies. Also, there's this whole other aspect that I didn't touch, that you have this wave breaking in the outer surf zone and it's injecting same sign vorticity across the entire surf zone, and that can roll up. Potentially, it was the initial hypothesis. So I just think this system's a little complicated in establishing the injection length scales. I think this is just a first go.
Can I ask a follow-up question?
Yeah. Yeah.
Unless somebody else has one. So you did your length scales in the alongshore direction. You looked at the longshore velocities. What about in the cross-shore direction? And is that dependent on how many waves you have in the surf zone? So the wider the surf zone, you would get different scales than if you had a narrow surf zone.
So I looked at I was in the crest-oriented coordinate system, and I chose to do that because then you have no FBR component in the alongshore direction. It's all going to be this cross-shore or cross-crest component. So I played kind of a trick here to get that. Does that help answer your question? So there's not going to be a alongshore component.
Yeah, so you showed at the end those velocity plots, which were amazing. You got rid of the crest, and you looked at the velocities, and you looked at the alongshore velocities.
Mhm.
I was wondering if you looked at the cross-shore variation in those.
Yes.
Your structure function, so you have an alongshore structure function. What about a cross-shore structure function? Is there any?
That's a good question.
That's what I was trying to get at, sorry.
Yeah, let's see. I did compute the cross-shore structure function, but I will say you can't resolve, I can't resolve like the full structure. The legs are really limited by the width of the surf zone.
So the width of the surf zone limits how big those eddies can get.
Potentially, yeah. I mean, I would say my analysis limits how far I can look in the cross-shore too, because I cannot resolve the velocities offshore of that. So I think some initial, like my hypothesis is probably limited by the surf zone width. I don't think I can show that at least the alongshore component seems to be about limited by the surf zone width. And so if these are perfectly rotational, maybe you could argue that, but yeah.
And I really like that figure, by the way. The middle one shows direct energy transfer. It's negative the whole way at 10 degrees, but you don't get that. The more short crested the crest, the waves are, the more that energy cascade occurs. Is that correct?
You
only
have
the-
much longer waves, and so my hypothesis, so I was actually very surprised by this result, and my hypothesis is that could be injecting length scales at much larger lengths for these really long waves. So potentially we're not seeing this clear energy transfer upscale and downscale. I will say that I'm showing you the surf zone average value, and if I look at each cross-shore positions across the entire surf zone, there is variation in the cross-shore. So there's more to the story too.
Thank you, appreciate that.
This is really interesting, and I did have questions about the longshore versus the cross-shore, but one of my other questions is, did you see any sensitivity, or do you anticipate any sensitivity to wave period? And would you expect a beach to be more vulnerable? For example, wave steepness may matter.
Yeah, well, so wave period, yes, I do think that will change a lot of these statistics because it's altering the number of waves that fit within the surf zone for a given wave height. And the numerical modeling example I showed you at the very end, she's actually looking at that in some of her, she looks at different directional spreads, but also added in different wave periods and did show that it varied with wave period. Your comment about the steepness, was it the steepness of the beach or the steepness of the waves?
Well, that was my next question, is they're coupled, right? So would you then look at it relative to air barren number or something, which will give you some measure of wave steepness and beach steepness?
Yeah, I think that would be nice to, I would say, expand some of that. Potentially that's something that could be targeted with numerical model. And there is some work for this perfectly uniform or planar bathymetry, where they looked at parameterizing transient rip current driven exchange, and they saw that there was some sensitivity based off of the steepness, because you're right that it changes the width of the surf zone. I would say to add in one extra element that makes this system that made the system complicated is that we have this bar feature, which is different than most of the previous studies that didn't have a barred beach. And so some of the things, the relationships that Emma is looking at with the numerical model are slightly different than what we expected based off of previous numerical model simulations with this perfectly planar beach. So I do think that both the surf zone cross-shore profile or the surf zone cross-shore profile is probably really important to the story.
Thanks, and just to take a play out of Tom's book, one more.
Yeah.
Did you see, you made a case earlier that the inner surf and the outer surf had very different profiles. And where was this inner surf? Do you see a different curve for these particular figures for whether you're inner surf or outer surf?
Yes, so the structure function in itself does vary depending off the position, where there's more, there's basically higher variance in the outer surf zone than the inner surf zone, which means at least for the second order structure function, your magnitude is slightly higher and then slightly lower in the inner surf zone. So the exact fit of the 2/3 is kind of varies, right? And I don't think I have the plot, but it's in the paper if you want to check it out. And this is actually consistent with some of Elgar's work in the field, where he used similar methodology and found that there's this cross-shore dependence in the structure function. And so
We saw minus 5/3 on average in breaking in bottom boundary layers, but if we looked at the evolution over a wave, we saw it got more or less steep depending on what phase of the wave you are.
that's interesting.
Thank you, really great.
Go ahead, Jean. Or,
Yeah. I noticed in the very beginning, when you set up your experiment, you control the bottom morphology with the concrete forms. Did you vary those positions at all at any time?
we varied the mean water level. So in a sense, we're varying the cross-shore position of it. Instead of like varying physically the feature.
Right, so you had long, straight features set continuously through the whole experiment. You didn't change them offshore at all.
Yeah, we didn't, but if you increase the water level, they would be viewed as like more offshore. I didn't end up looking at those trials a ton where we say we lowered the water level because I guess we set it up and so that the wave breaking would trigger right at the wave crest to maximally get the surf zone width. But I would expect some variation. I can't say I looked into that in detail. I mean, there's a lot of interesting things you could do with changing the bar too, and like maybe pulling out a bar to look at alongshore varying bathymetry too.
Yeah, I mean, if you look at any given shore face, it's not linear. There's variability in shape to it. I'm wondering if that would have an effect.
Yeah, I'm sure it would. It'd be interesting to look at.
Thank you.
I mean, yeah, go ahead.
No, if you have, nobody else wants to. Okay, no.
He's been trying to ask for a while.
No, he's been trying to ask for a while.
There's a hand up over here.
Well, was someone going over here?
Question over there.
Okay. No, I was actually pointing her at you. You've been trying to answer for a while.
Behind you. So my question is, assuming that the roughness of the bottom affects the process, the breaking process and the energy of the rip current, like in your experimental model, you didn't take that into consideration as I understood. So how likely your model does like represent the reality?
How likely does it affect the nature? So yeah, we had concrete system So this is the lab. It's not perfectly going to represent nature. I think bottom roughness is one aspect that may differ. And that might change like dissipation of wave energy. So in the perfectly turbulent system, you have some of the limiting of maximum length scales of eddies is actually based off of dissipation. You can also see that at the small scales too, probably. So that might change. I think one thing that I thought was interesting to look into is the fact that we have boundaries in the lab, and so that does change the dynamics. It led to like a very weak mean current near the sides of the walls, which is why I focused on the center of the lab for this analysis. And so yeah, I think that there are some differences, and I think that some work is being done in the field to explore this. It's just hard to get these being able to have this perfectly incremental changes in wave conditions. So I hope that there's more work in the field to explore this. Yeah. Okay.
So I mean, this is like GFD playland here. One thing that strikes me is how relatively circular these are. Can you go to the wiffle ball ejection picture? As the eddies go out, and they're presumably barotropic and they're being stretched, wouldn't you expect them to spin up just as their height gets taller and their width gets smaller? And how does that fit with what looks like a linear ejection?
Yeah, so no, I think that's a good point. Thinking about, okay, these eddies are being ejected onto the shelf, what do they do? And they probably start dissipating because they, in more of a 3D system way. This, I would say, how I've framed it at least is that the surface, the bar crest is right here. And so if you kind of like squint your eyes a little bit, it's kind of flat through that system. And then it drops off fairly dramatically off of out of the surf zone. And so maybe there's where we would see that. I can't really see that very well, but maybe I could track wiffle balls.
If you looked at like the magnitude of the relative vorticity, do you see it increasing at all as you go offshore, or does the dissipation eat it up before the stretching can accelerate it?
I would say the magnitude of vorticity. So I see that there's more. I think I might have this one.
For the numerical model, yeah.
Well, the numerical model is one way to look at it, so I can play that if you'd like.
So it just gets dissipated very quickly once it gets ejected out.
Yeah, and this should represent that process. It's depth averaged, so it's not, but it should still represent that potential vorticity, right? So you can see that in the system. I would say in the lab, I was so limited to the surf zone. And so I couldn't say too much. This is my little, this is the RMS of U prime and V prime. And so actually I couldn't see that much variation. I mean, this is not looking at individual eddies, but I would say maybe in the lab, if we tracked the wiffle balls, we could say something about that. And I think that's really interesting to think about. Or maybe the model would be helpful for that. Oh, here's my cross-shore dependence. If you want to get into that more, but yeah.
Mine is more about the application of your findings. You said that one of your students is comparing it to the NOAA predictions, and are those predictions, is it able to separate the transient versus the bathymetric rip currents? And then is NOAA the only model out there for rip currents right now, or are other places using other models?
Yeah, that's a good question. So a lot of our numerical models can simulate rip currents, but NOAA, at least in the US from my understanding, is the only, I would say, predictive model that they have just on a daily basis, estimating like what is rip current hazards, and they do it like for swaths of like all of the East Coast if you look it up online. And so it's actually, it's like a linear regression, basically. They just like show like, okay, if you increase wave height and you do some other things that we think are related to bathymetric rip currents being more likely, then they say it's more likely to have hazardous rip currents. So it's kind of simple in the sense that it's actually not simulating like the actual beaches with like the type of model that I show here. What I was working with the student is the fact that the NOAA hazard rip current model is actually really well, it's trained based off of observations that were in the Outer Basin, North Carolina, which is, I would say, kind of notorious for having lots of gnarly bathymetry and thus bathymetric rip currents. And so the argument here is that we actually don't know if it can represent different, like hazards from different types of rip currents. And so the goal there was to, just give a first shot at seeing if it could actually, if it was predicting high likelihood of hazardous rip currents when lifeguards, for example, were observing both transient rip currents or bathymetric rip currents. And then I was explaining the parameterization, which for bathymetric and transient rip currents, which is based off of our physics-based understanding. And so you could, make some arguments to claim when we see hazardous rip currents based off of those. And so she's basically saying, at the beach she looked at, she didn't see that NOAA's rip current hazard model really had a lot of skill at guessing when we see hazardous transient rip currents based off of our parameterizations.
The US has pretty high rip current deaths compared to some other countries like Australia even. So it'd be kind of interesting to look at the models that they use and see if they're more accurate or fit closer to your data.
Yeah, no, that's a really good point. I would not say I'm an expert at how they do it in Australia, so.
Is there questions from the audience? No online questions, so, hey, with that, let's thank Christine again.